What example? What do I do? Oh, right, sorry. I'll try to scroll down. I'll try to scroll down. I can't scroll down. I keep pushing. Yeah, I can't do that. I stop at a certain point and I realize. Yeah, it's stuck. Yeah, that number one. All right, let me just, okay, all right. You there now? God, I can talk now. All right. What the mic is working today? Oh, the studio mic? Hope not true. Okay, good afternoon, Kevin. Okay. I'm fine, you? Okay, I sent information to your tutor. Your tutor, which you should have tutorial on Mondays. Did you see the tutorial I sent?
Which one would that have been, sir?
Pardon me?
What number would that have been?
1. And I sent 2 as well, number 2.
Yeah, we have 1 and 2.
Which you should start you should start it by maybe, I don't know if he's finished 1 as yet. Or is a female maybe. What's the name of the tutor? Tutor. I don't know if it's the right person. Is it Nikisha or something?
Yeah.
Okay, so it's a female. Okay, it's Nikisha. Okay, all right. I sent it to her, so she should have added it. I'm going to start what is called the proofs today. I actually upload online the solution to the what I've discussed last week online, which is the propositional function using the negation. You should see it online on OURVLE. So we'll be doing today what is called the proof techniques. Okay, so more now, let's start now. We're going to start now what is called the first one we're going to discuss. Yeah, thank you. The first one we're discussing with you today is called proof by what is called counterexample. This thing I'm moving a little slow. I don't know. I want to. Yeah, wait, hold on. You hold on to this thing. You hold it down. Oh, all right. Thank you. Okay. I don't want to be the man. Okay, are you seeing now? Everybody seeing the presentation or the PDF presentation? The first time we're teaching you, ladies and gentlemen, is how to prove a general statement. Now, we have what is called a counterexample, which is what we use to disprove a general statement, right? So a counterexample is just an example, as the name suggests, an example that we can use to disprove a general statement. So what am I saying? We normally use a counterexample. Listen carefully now, everybody. We normally use a counterexample to disprove statement of a general form, like we say for all. All men are dogs. What would be a counterexample? That gentleman is a man and he's not a dog. What other example could have used? All prime numbers are what? Are odd. What would be a counterexample? 2 is a prime number and 2 is not odd. Are you with me, Kevin?
Yeah. Yeah. Wait, sir, question. No, sir, you hear me?
Okay, guys, let's go now. Now, to prove for all, what we normally do. Listen carefully.
I had a question earlier.
Ready? Normally, to prove for all, what you have to do, you have to show that in the domain, whatever the domain is, we show that it's true for all x in that domain. So I'm showing what we normally do generally. To prove for all, we show that, because today I'm going to do the proof techniques. I'm going to show different proof techniques. What are the proof techniques I'm talking about? I'm going to do what is called proof by counterexample, proof by what? The direct proof, proof by what? Contrapositive, and proof by what? Contradiction. Okay. Okay, so to prove a general example, to prove a general statement, we try to what? Show that it's true for all. Okay? Now to prove there exists something, if we can find an x that holds true for it, we say, okay, we can prove it by showing that it is true for a particular x or a particular whatever that situation is. So to prove for all, we show it's true for all x in the domain. To prove there exists, we can find a particular x which holds true. Now to disprove now for all now, listen carefully now. Now here comes my counterexample, ladies and gentlemen. To disprove for all, if you can find an example for which it doesn't hold true, then that's our counterexample. So to disprove a general statement, we use what is called a counterexample. And then to disprove now, there exists, we show that it is true for what? It is true for all x, or I mean false for all x. So the first one we're talking about now, guys, is counterexample, right? Okay. No, every prime number, but I said that one already. Well, it's a different way. I said that let the propositional function, which I call p of x, which it depends on the value of the variable x. That's why I call it p of x. Let it be the propositional function. Every x is a prime number for every integer x. We know so that every x is a prime number. We know it's not true. So that is an example I'm talking about now, where you can choose any number, which is say that is a what? An integer, because first your premise is that it has to be an integer, right? Right? Now 4 is an integer and 4 is not prime. So 4 will be our counterexample, right, ladies and gentlemen? Are you with me, Kevin?
Yeah. Yeah.
I don't know. Yeah, and I realized I didn't respond each time. I realized I was wrong.
Kevin. I'm Kevin.
Sorry, calling us?
Can you hear?
Yeah, we can hear you.
Thank you, thank you. Okay, are you with me, Kevin? You understand what I just said a while ago?
Yes. Yeah.
Okay, good. Let's move on then. No, we don't need more. We just need one. Okay, all right. The next one I'm going to talk about today, listen carefully now. Okay, we have this kind of direct proof, all right? I'm going to prove it directly. No, but the one I'm going to show now how to prove a statement, like say, a if-then statement, P implies Q. Because we can also prove a general statement, like say, root 2 is irrational. That is a general statement. And there's no if-then, right? So the first one I'm teaching you to prove now is called a if-then statement, P implies Q. Because I could also ask to prove, like for tutorial 2, that was the last question on tutorial 2, I think. I think it was number 7 or number 8. I said, prove that root 2 is irrational, or I think it was root 3. Yeah, very good. Thank you, my friend. Prove that root 3 is irrational. I could have done by way of direct proof. I could have used a contradiction, which we're going to talk about coming up soon. That's a general statement where there's no if-then. But when I'm talking about this now, I'm talking about how to prove something implies something. If P, then Q. P implies Q. Now to prove a statement of the form P implies Q, because I just said, first thing first, listen carefully now. Because I can have to prove something that's not an if-then statement, or I could have to prove an if-then statement. What do we normally do? Now we have to bring in now some theorem that we know. That's why I mentioned about integers. All right, Kevin, what is an integer, Kevin? What are integers?
Numbers.
What are integers?
Numbers.
All numbers.
Oh.
Integers are all numbers. What are all numbers really?
All numbers.
The reason I need to know because there's no way you can prove what we're going to prove now unless you understand what integers are. First, we have natural numbers, which have like natural numbers, counting numbers. Then we have all numbers, which comprise of natural numbers, 0, 1, and so on, 1, 2, 3. Then we have what is called integers. Now, integers comprise of what? All numbers and what? And what? Negative natural numbers. So if you think of a number line, that's really integers, -4, -3, -2, and so on. Now, why am I talking about integers? Because the only way I can prove what I'm going to prove today is that you have to understand what integers are. Okay. The next thing, Kevin, what are even numbers, Kevin? If a number, how can I express an even number?
A number that is divisible by 2 without a remainder.
Having said that, then is 4 an even number?
Yes.
Is -4 even? -4 even number?
Yes.
Okay. Is 0 even?
Yes.
Okay. So every even number can be expressed as 2 times k. Where k has to be a what? An integer.
Yes.
So -4 is even because -4 can be expressed as 2 times minus 2. Where -2 is what? An integer. 0 is also even because 0 can be expressed as what? 2 times 0, where 0 is an integer. Now what are odd numbers now? Odd numbers what? Is -7 odd?
Yes.
How can I express -7? How do I know -7 is odd? How can I express it? As 2 times what? -4 plus 1. Every odd number can be expressed as what? Even plus 1. So 2 times k plus 1. Where k has to be an integer. Because every time I ask people in an exam, people don't understand the concept. That guys, when I talk about integers, don't confuse the fact of integers now when I reach with natural numbers. Because to prove by induction, which I'm coming up, that's next proof we talk about it today, the one that is a killer one, people always confuse natural number with integers. When they're talking about the proofs, this is what I'm talking about as time goes by. Don't forget that, guys. To prove what I'm talking about now, direct proof, proof by contradiction, and proof by contrapositive, we need to know what integers are. It's what we have to prove it correctly. So listen, now that we understand each other, now you must always, to prove P implies Q is in direct proof, we prove that what? That the statement is always true whenever what? P of x is false. Why? Why? Because false followed by anything is always true, right, guys? Now, what you normally use to prove directly, to prove something directly, we use some accepted axiom that we know from elementary stuff. We use the idea of natural numbers, integers that we already know that are true stuff. That's why I mentioned about integers first. So we use a statement that we know mathematically is true already, that we actually infer to something that we know that was always true. And we use these inference in our proofs. That's why we prove things directly. What does that mean? Look. Look. So that's what I mean, guys. So we use some theory that we already know. So some mathematical theory that we know is true, we use them back in our proof. All right, so I have an example to do for you. Let me just go to different example now to have. So I have to come out of this one and go to a different one now. Okay. So first I'll talk about a counter example right there. All right, so let's see, guys. Let's stay with me. I just think I'm not doing this thing properly. Okay, that was my first counter example. Every prime number is odd. I just mentioned that a while ago. Now, to prove no direct, let's do the example for direct. No, do you have to leave? You're bored? Oh. No, to prove you can stand there, so finish. Now, to prove something directly, to prove it directly, guys, look at this example now. Now, in the exam now will tell you what to use. If the exam don't tell you what to use, then I guess you can use whatever you want. But the order of the exam is such that the examiner wants everybody to have the same solution to make sure you can gauge it. So we always want to use the same proof technique. So if I say prove directly the statement, which statement? If x is odd, then x squared is also odd. Now, is that normally true? Is it, if x is odd, is the square also odd? If x is like, say, 5, what is x squared? 25. So if a number is odd generally,
yeah, true.
the square, so that's true, right, Kevin?
Yeah.
Very good. But guys, the point now, listen careful now, guys. The point for these proofs, guys, Mona, everybody listen to me careful now. The points for this proof is not to determine if it's true or false. These statements are generally true statements. The student who listens the most learns the most. These statements are generally true statements. However, the examiner wants to see if you can demonstrate by some way of some proof techniques or to prove them mathematically. Let's try to prove this now. That if x is what is odd, so is also the square of x. Let's see, how do I prove it? I first start by saying, if x is odd, look, I can always express as what? 2p plus 1. But be careful now, guys. But you have to tell a man that where p is an integer, not natural number, integer. Where p has to be what? An integer. That's a very important part of the proof. That's going to lose marks. Yeah, but look. But the man said x squared. That's why I now say x squared is equal to. Because you first establish your premise that x is what is odd. And because x is odd, I can express x as what? 2 times p plus 1. But the man said by the conclusion that x squared is odd. So you must show him what x squared is. So x squared is really 2p plus 1 r squared. Good to go? You expand that, you expand it, and you get 4p squared plus what? 4p plus 1. Good to go? But look. But every odd number, the battery. Every odd number can be expressed as 2 times something plus 1. So for 4p squared plus 4p plus 1, I can remove a 2. I factor out the 2 because I'm not showing the man that x squared is odd. So if x squared is odd, then x squared can also be expressed as 2 times something plus 1, where this something must be an integer. That's why I actually factored a 2. And then when I factor the 2, what do I have? I keep the 1 outside because I want to see the plus 1 outside. So for the first 2 terms, which is 4p squared plus 4p, I remove a 2, which is common. And what do I have in bracket? 2p squared plus 2p. But to get full marks, what must be true? 2p squared plus 2p must be an integer. That must always be true. Don't forget that, guys. If you leave it off, I'm going to leave off your grade. Don't forget that. Because every odd number can be expressed as 2 times something plus 1, where the something must be an integer. Everybody appreciate that? That's why I know that now that what? X squared is really odd. Because I've shown that what? X squared is really what? 2 times something plus 1. Where the something in bracket is an integer. How do I know p squared plus p is an integer? I mean, how do I know that 2p squared plus 2p is an integer? Because p is an integer, p squared is an integer, 2 times p squared has to be an integer. And if I add an integer to an integer, I get another integer. Because it's said to be close and addition. Right, guys? Okay. Do you understand what I'm... Mona, do you understand Mona? Anybody have a question? You understand, Kevin?
Yeah.
Okay, very good. We can move on then. Mona, any question? I didn't hear anybody say yes or no. You didn't answer, I don't know. Do you understand now, Mona? Can I move on to the next proof technique? Okay. The next one I want to do, ladies and gentlemen, now. Let's see the order, which way would I reach now? The next one I want to do for you now is called proof by, the battery's low, they said, what's going on here, man? Proof by contradiction. Come guys, pay attention now. The next one is called proof by contradiction. Now, what I'm going to show now, listen carefully now. Now, there are 2 different types of statement. You have a statement that has no if-then, and the one that has an if-then. Why am I bending down like this and the mic not working? No. We can prove a statement that is no if-then. Like say, prove that root 2 is irrational. Or we can prove a statement in the form of what? P implies Q. So I'm going to show you to prove that one today, which is P implies Q. But look, guys, to prove a if-then statement using contradiction, what you normally do, we assume that the conclusion is false. Yeah, man, look. We assume that what is the conclusion of P implies Q? Q is a conclusion. We assume that Q is false. So instead we prove P implies not Q. Come again. We assume that the conclusion is false. So we prove P implies not Q. At the end of the day, guys, listen careful now. At the end of the day, you do the same exact thing. You use mathematical knowledge you know about even numbers or whatever it is at the time, or the mathematical axioms. And then now you're gonna realize that, listen carefully, you're gonna realize that your assumption was really false. Hence a contradiction. You're gonna realize that your assumption was really false. Hence a contradiction. So if you don't understand what I mean, I will show the example. I think this thing is giving me, I don't know why this is not moving, guys. Why it's not moving? Oh, let's see, it's not moving. It's really, okay, right. So it means that then, because Q of X was really false then, it really can't be true, or whatever the vice versa you said it was. So it means that the original statement was indeed true. So if you assume that the conclusion was false, you're gonna realize that of a truth, it was really true. It was really true. It was a contradiction because your assumption was not really right. So let me give an example, and then the example show what I'm talking about soon. So guys, please, you must go back over your notes, guys. Please go back over your notes. Let's look at the example now of a contradiction now. Look, guys. Prove using contradiction, that's example 3. Prove using contradiction that if n is odd, look, guys, if n is odd, then 5 times n plus 11 is even. No, we're not here to determine if it's true or false. Oh, that might not work. No, we're not here to determine if the statement is true or false. Those statements are what? Normally true statements. No, that is really true. That if n is odd, 5 times n plus 11 is even. No, that is true. Think of an odd number. 5. 5 times 5 is what? 25. Plus 11 is what? 26. So that is even, though. So these are normally true statements. But what I wanted to demonstrate to me is that you can prove it by way of what? Contradiction. Ah, but look, guys. Look, pay attention now. Look, pay attention. Look. No, I'm going to call now P. It's an if-then statement. I'm going to call P what? The first thing. What do I call P? That what? That n is odd. What do I call Q? That 5n plus 11 is what? Is even. But remember that we are proving by contradiction an if-then statement. And you're told that you must prove instead P implies not Q. So what do you mean not Q of that? Not Q of 5n plus 11 is even is what? Is 5n plus 11 is odd. Are you with me, Kevin?
Yeah.
Very good, very good. Are you with me, Mona? Because not Q would be 5n plus 11 is what? Is what? Is odd. So instead, guys, listen now carefully. Instead, we are proving instead, listen carefully, guys. So instead, we prove that what? That if n is what? Is odd, then 5n plus 11 is odd. That's what we're proving instead. Right? Okay, very good. Let's start the proof now. Let's start the proof. The man says if n is odd. Now, if n is odd, I can express every odd number as 2 times something plus 1. So I can call n what? 2 times r plus 1, where r has to be what? An integer. Good to go? But in mathematics, guys, you must do what the man says. The man says 5n plus 11. That's the premise. I mean, that's the conclusion. Now, 5n plus 11 can be written as what? 5 times, oh, not 5n, 5r, I mean 5r. Can I use r? Do I use r instead? I use r? No, I use n for that, sorry. 5n plus 11 is really what? 5 times whatever n is plus 11. But n was equal to what? 2r plus 1. So we're actually using what? We're actually substituting for what? For what n is. Come again, let's go again. Look, the man say n is odd. So n being odd can be written as 2 times something plus 1. 2r plus 1. But the conclusion says 5n plus 11. Let's see what it is now. But 5n plus 11 is 5 times n. But n is what? 2r plus 1. And then put what outside what? Plus 11. When you do the algebra, you get what? You get 10r plus what? Plus 5 plus 11. Then when you do the algebra, now you get what? 10r plus 16. And then 2 is common to both. The common factor is 2. So get 2 into what? 5 what? 5r plus 8. Ah, but look, but 5r plus 8 must be an integer. But what you realize, guys, if you have 2 times something, which is even. So our assumption that 5n plus 11 was what? Was odd, was indeed false. So 5n plus 11 should have really been even. Hence the contradiction. You guys don't pick up what I'm saying? You understand? Do you understand, Kevin?
Yeah. Yes, sir.
You sure? Because guys, because we assume that it was what? It was what? It was odd. It was odd, we assume. But we have shown that it became even. So our assumption that 5n plus 11 was what? Was odd, was indeed false. Because hence a contradiction. It should have been even. So our original proposition was really true. That 5n plus 11 is what? Is even. Hence a contradiction, guys. So look at what I wrote for my conclusion. That's my T there. All right, let's see what time is it now, because I think we have to stop here. Oh, we still have time. We still have 9 minutes. We still have time. Then the last one, guys. Okay. So Mona, still understand what I'm saying, Mona? The last one now is proof by what is called contrapositive. I'm not seeing the thing. Where is the thing to click? I'm not seeing the thing to click, guys. I don't know where it's not coming up. Where's the contrapositive proof? It's not coming up at all. Hold on, guys. Oh. The last one, no, ladies and gentlemen, is to prove what is called the contrapositive. Now, if you realize that all I'm doing today is the P implies Q, I keep doing the implication today, right? Okay, so again, okay. Now you have been taught when we were doing the truth table that the contrapositive of P implies Q is not Q implies not P. So to prove something by way of this contrapositive, no, don't forget, no, ladies and gentlemen, that the contrapositive of some implication is really what? The same thing we are saying, but in a different way. And there what is said to be logically equivalent. What am I saying? P implies Q is logically equivalent to its contrapositive, not Q implies not P. So to prove P implies Q, if it was an if-then statement I gave you, it will first convert to its contrapositive. Why? Because we're proving by what? By contrapositive. And then we prove it in a normal way again, as if we know what it was. And then, so what it really is, guys, the proof by contrapositive is an alternate. It's an alternate proof of the original statement. At the end, whatever we said it was, it would end up being the same, because we're actually proving it another way, really. Nothing more. Are you with me, Kevin?
Yeah.
Okay, good. Let's go to the example. Okay. The last example say part 4. Prove using contrapositive that what? That if x squared minus 6x plus 5, please, guys, come again. Prove using contrapositive that what? That if x squared minus 6x plus 5 is even, then x is odd. Okay? No, but don't forget now, guys. We're going to prove it a different way using what is called the alternative proof. So we're going to prove not Q implies not P. Now, I first call P, what I call P first. I call P x squared minus 6x plus 5 is even. Or call Q x is odd. Sorry. Now, the negation of not P in this case is what? I mean, negation of P is what? Is what? X squared plus 6x is odd. The negation of Q is what? Is X is even. But our original proposition was P implies Q. But we prove instead not Q implies not P. Now, based on what I just said a while ago, what about our not Q implies not P? If X is even, then it's odd. So we start by different. So the premise becomes the conclusion in a different way. It's like we negate it. So don't forget, guys, we are using the contrapositive, right? Instead of proving P implies Q, we are proving not Q implies not P. So we start by saying, now, what is the not Q now? The not Q is this. The not Q is what? X is even. Now, if X is even, how can I express X? 2 times M, where M is a what? An integer. But the conclusion of that not P now, what is the conclusion? Not P. What is not P? It was what? It was x squared minus 6x plus 5 is odd. Let's see if it's true now. So I haven't found what X is. X is 2M. So x squared now minus 6x plus 5 is what? Substituting X for it to be 2M. So it's 2M all squared, so I did the substitution. Minus 6 times 2M because X is 2M. And so on. When you do your calculation, you end up getting what? Because the idea to show that it's really odd, it's odd, right? So every odd number can be expressed as 2 times something plus 1. So I factor that 2, and I end up getting that. So we show that it was really what? It was really odd. Well, do you understand, Kevin?
Yeah.
If you don't understand, I guess just please go back over the notes and try to understand it. And we'll talk about it tomorrow.
Yes, sir.
All right, Kevin. Okay, any question before I leave, Kevin? Any question before I leave? Mona, I cannot hear Kevin. Could you just exit quietly, please? Let's see, Kevin, you have any question before I leave?
No.
Okay, all right. So tomorrow, Kevin, tomorrow. Okay.
Let me play this video first.
Hopefully, if not tomorrow, by next week, should be. But the thing is that he won't be in this room. Sorry. No,
But doesn't have to think like, don't worry.
no, man. I'm going to explain to you. Yeah, hurry. I can't. All right. The thing is that, sir.
Yeah, thank you.
Um,
No, it's gonna
Yes, sir. We talked to you, guy. Yeah. I said, we talked to you.